suppose this is f, and we get some kind of maximum frequency involved, maybe the basis function. We might have, a bunch of different functions out here in this range because we have different messages being transmitted, but they're all, let's say, up to some maximum frequency. Now there's going to be some noise in this range that we capture with the basis functions that represent this signal. And then there's going to be some noise outside of that range in 2 of f that's irrelevant. It doesn't help us. It's noise that's uncorrelated with the noise in band, and it's at different frequencies. So run it through a low-pass filter and get rid of that extra noise. We can throw it away. Those match filters in this case are basically a set of low-pass filters, or at least a set of filters that don't pass any energy, whether they're low-pass or band-pass. They're all in this region. TB, if I could have the overhead. They're all in this region here between my fingers. They have no content in that region itself. So that is basically the concept here on the additive white Gaussian noise. Okay, good news. Our demodulator at least works for this case. And as I said, I have a trick. It's the reversibility theorem if I actually have colored Gaussian noise. Now what the first thing I'll do is run it through a one-to-one transformation that whitens the noise, didn't lose anything, and then apply my maximum likelihood detector theory to that. Okay, so let's look what that maximum likelihood detector actually does for the additive white Gaussian noise channel in particular. And it's got a nice simplification that occurs. We kind of have these probability distributions that were nice mathematically earlier, but what do they mean? Well, for the map detector, the form of that detector is basically maximize the function e to the minus 1 over n naught, the received value that we got minus xi squared times the probability of the input. This is a map detector. You'll notice I threw away 1 over square root of 2 pi sigma squared out front, or 2 pi times n naught over 2. Well, that's just a constant term. It's not a function of I, so no reason to include it here in the maximization. Furthermore, I had minus 1 over 2 sigma squared. If sigma squared is called n naught over 2, then fine. Okay, that's 2 times n naught over 2 is n naught. And then the probability of y given x for the additive white Gaussian noise channel is pretty easy. It's just, if I'm given x, the probability of y is simply the probability of the noise evaluated at the output y minus x. So here's my noise up here. Now I have a vector Gaussian noise with just a product for white noise of all the independent terms. Okay, so I'm going to have a product, okay, of exponential factors, and we know when we have a product with exponential factors, we can add the exponents. So what I've done here is essentially I have abbreviated that sum of products as the sum of squared values, which is the norm of the difference. And I've done that for a particular reason, because you can see this is kind of easy to interpret. This is basically the distance squared between the received value and point I. And clearly that's going to play a major role. And that is very intuitive. Without any theory, if I'd asked you to decide which message was transmitted, you would have probably picked the point that was closest to the received value. And you can see that's going to be very important in maximizing this function. The closest value here, since there's got a minus sign here, is going to maximize this function outside of the additional probability that's here. So if I were doing an ML detector, I'm there. Instead of maximizing here, I could actually eliminate this term. If I maximize this, then it minimizes this distance, and so I could actually write it's minimized over all the possible transmit vectors v minus xi. Well, that's pretty nice. Okay, I just picked the closest point. You can do my decision region. Somebody asked me if I could pre-compute the decision region. This is pretty easy. I've got a nice looking constellation that looks something like this with points out here in the corners. Well, the decision regions are just going to be obvious. They're the 4 quadrants. Okay, so I'll just look at the 2 match filter outputs, decide what quadrant I'm in. I get a maximum likelihood decision. Minimizes probability of error if each of the messages were equally likely in this case. For the map detector, if I actually take log of this function, log is basically a monotonically increasing function. So if I'm maximizing a function, I take log of it, I can maximize the log and still get the maximum value occurring at the same point. If I take log of this function, get rid of the minus sign, then the map detector is almost the same form. It's got that nice distance term in it, but what happens is it gets augmented by a term that if you work through the algebra turns out to be n naught natural log of the probability distribution. So there's a little bit of an offset, so it's not quite picking the closest point. If I know one of the points is more likely than another, I'm going to weight it a little more heavily in my decisions. One of the points in the extreme had a probability, a very high probability with respect to all the other points. It's essentially going to cause some deviation from that simple pick the closest point rule. So the map detector is a little bit harder to do. The ML detector itself, if the messages really are all equally likely, that becomes very easy. Okay, pick the closest point detector. Okay, so let's look at some examples of this for transmission. In fact, I already drew one there in a corner, so I jumped ahead of myself a bit. But the simplest example would be a one-dimensional transmission system. So capital N is equal to 1. And what I'm going to do is transmit one of 2 points that are same magnitude but opposite in sign. So about as far apart as I could get them. Well, if they're both equally likely, what the maximum likelihood rule is going to be, this is the decision region over here, and in fact we're only on the horizontal axis with our values. Easier to draw it that way, but anything to the right of 0 or anything positive, I choose x1. Anything negative, I choose x0. That's a pretty easy rule. Okay, so this would be the ML detector. Now what actually happens for the map detector, if I knew that actually x0 was a little more likely than x1, let me draw my line here again. This might be 0, but if x0 is more likely, then basically I'm going to push out its decision region just a little bit, depending on how more likely it is. And this difference here works out to be sigma over x1 minus x0 norm, not squared, log of p of x0 over p of x1. So there's a little bit of an offset for the 2-point constellation if one of the points is more likely. That makes sense. Okay, if 0 is more likely, then, and the more likely it is relative to 1, then I'm going to push the decision boundary over. And so more times I'm going to decide that x0 was transmitted. So that's the map rule here. And of course, if they're equally likely, you can see that this term here is log of 1, which is 0, and so the offset is 0. That makes good intuitive sense. Yes, I can. There you go. So this is the offset. That little distance right there is this term. Now, there is a alternate form in the notes. I'm going to start on a new page here of the map detector. And sometimes this is preferred. And again, after some algebra, which is in the book in detail, you can determine that the map detector actually maximizes over the choice among all the transmitted signals the inner product of the received vector y and the input vectors xi in the signal constellation plus some constant ci, which is not a function of v, the output of the channel, so you can pre-compute it, and ci you can determine is n naught over 2 natural log of the probability, the ith point, minus the energy, essentially, the squared norm, the ith point, divided by 2. You can clearly see this depends only on the input, so it could be pre-computed. And basically, this has a kind of a nice form in some situations because we have this dot product occurring. And you recall that trick we saw in math earlier where we could actually take the inner product and replace it by a filter. And in this case, it'd be y of t, which corresponds to v on the input. But instead of having the basis function reversed in time like we had earlier, now we have xi itself there. So I would have a match filter to xi itself, sample at time t equal to capital T, and what would come out would be y dot xi. Now, if it were the case, and it sometimes is true in transmission, depending on the signals, that they're all equally likely, and they all have the same squared length, then this CI term is the same for all the points. So I could ignore it. And so what I would do would be take the signal y of t and run it through a bank of filters matched to each of the transmitted waveforms and pick the largest one, would be the map detector rule in that case. Also be the maximum likelihood rule because all of these terms would be the same. That means they're equally likely. That may be easier to do in some situations than going through the bank of filters matched to the orthonormal basis functions. Usually that's not the case in transmission these days, but some of the earliest types of transmission systems, they attempted to just do this directly. It's a little simpler implementation this way sometimes when the number of transmitted signals is very small. Classic example of this is something called frequency shift keying, which is almost never used anymore in transmission. There's a few, if you've got an old pager, they use frequency shift transmission. What frequency shift is, they have two different frequencies for modulus. So one of the basis functions is centered, it's a bandpass filter at one frequency, and the other basis function could be a bandpass filter at another frequency. So you look at that and you say, well, I have only two signals I'm transmitting. One's at one frequency, one's at the other. Why don't I just run it through the two bandpass filters and see which one has energy at the output, and that's I decide either 1 or 0, depending on. And that would correspond directly to this type of transmission. Okay, so we really don't even have to worry about the basis functions or any analysis in that case. That's a very old modulation technique. As we'll see later, it's not very efficient, so it's not used anymore. Kind of wastes bandwidth and energy to transmit signals, FSK. Very easy to construct the receivers for it. Okay, so those are the ML and map detectors. Now, there's a couple of properties that are going to be useful to us when we have additive white Gaussian noise for these detectors. And the first one is called translational invariance. Sorry, not independence. And it's a pretty simple concept. It says, if I take each and every message in a signal constellation and I translate them all by the same constant vector, so it is not a function of I, then this implies that there is no change in probability of error. Now, hopefully, and these are for the maximum likelihood detector. So we're assuming that all of the inputs are equally likely. Now, I would hope that this would be kind of obvious to see that if I had a signal constellation of any type and I have noise that's centered on each point that's transmitted, okay, then translating each and that noise, no matter where I translate a point, okay, is the same. than whether I have a constellation that looks like this or whether it's like this and has decision regions that look like that instead of these decision regions. Because as long as the noise that's being added is the same, then the probability of error does not change. Yes?
We're still talking about, this is just for the additive white Gaussian.
This is still for the additive white Gaussian noise channel, because this is definitely not true in general. So thank you for emphasizing that point. For additive Gaussian noise, this is actually true for any whether it's white or not, this particular theorem. But in this case, we're actually in the additive white Gaussian noise section, so you can think of it as additive white Gaussian noise. You translate the constellation by any amount, then you don't change the probability of error. And why would that be true? Well, what I'm going to have now is x plus a being added to the same noise, n, producing some other output, we'll call it y tilde. And basically what's going to happen is that this output here, any v that originally came out of the channel where an a was 0, is now going to be offset by that same a. And what happens is if I look at the difference between v and xi, which was critical for the maximum likelihood detector, if I add a to this term and I add a to that term, it subtracts out. And so I have exactly the same probability function that's describing what's going on in the translated constellation. And so therefore, since the probability of error is ultimately going to be a function of that probability of the noise, or that conditional probability that represents a channel, and that's the same, then whatever it is, it would have to be the same if I translate each and every point by a constant vector. Okay, so if you happen to see a constellation in your homework or your endeavor anywhere that looks like a translated version, and you're dealing with additive white Gaussian noise channel, you already know how to analyze it if you know how to analyze the first system. Yes, sir?
Yeah, back to this comment about, it doesn't, it works for Gaussian if you switch it. If the noise is additive, I don't see why the distribution would matter of the noise if you translate it or not.
If that's true what you just said. Now, did I say something different from what you just said?
You said it's not true in general if you don't have Gaussian noise?
It may not be true.
I don't see why.
Well, if you had some kind of weird, distribution, let's suppose I'm trying to think of a distribution for which that would work, but if the noise were not additive, then it, like multiplicative or something, then clearly it's not going to be true, right?
But if it's additive,
If it's additive, that's a good question. I tend to agree with you on it. I can't see immediately any exceptions to that. I bet we could probably prove it. Here, this translational invariance is being presented in the context of the additive white Gaussian noise section, so it's definitely true for this. I think you're right. It may be true for any distribution, as long as the noise is additive, because basically we're going to get what happened here. This is a function of the additive channel. We're going to add to the output the same thing we added to the input, and no matter where that argument occurs in, P of y minus x of some noise, no matter what that noise is, if it's additive, then if I've got y plus a minus x plus a, the a's are going to cancel. I get the same distribution. I think we just proved your theorem there. So thank you. So that's true in general for any additive noise, but here we're interested in the additive white Gaussian noise. Now, one that will not be true for any additive noise, but is true only for additive white Gaussian noise, is rotational invariance. And rotational variance, let me draw a picture of it first before I write down what it is mathematically. If I had a constellation like this, because the noise is kind of equally projecting with variance n naught over 2 in all dimensions, if I were to look at the corrupted signals, it doesn't really matter what angle I look at from any different point, okay, in the constellation. I draw out any angle radially, the noise kind of looks the same in any dimension. And that's independent of where the points appear in a constellation. So if I were to rotate the entire constellation so that the points, let's say, were 45 degrees away, we still have these circles like this. And you look at that and you say, well, gee, you just changed the axis labeling for the system. You haven't really changed any of the dynamics in the system, because the noise doesn't really depend on the signal. It's added to it, and it's nice and spherically symmetric. Now, if the noise were not spherically symmetric, it would depend on the basis, okay, and I couldn't rotate the constellation and necessarily get that nice circular symmetry. So if it's white and it's additive, you can rotate the constellation by any angle and you will get the same performance. Mathematically, how that's represented in